This course is about acids and bases, many reactions and phenomena in industry, agriculture, living organisms, and generally in nature are closely associated with acids and bases. Therefore, this subject is very important in both theoretical and applied chemistry, and students should be well familiar with this subject. My aim is to cover basic and the most common concepts of acids and bases in these online tutorials. At first, we should discuss what are acids and bases, which substances are regarded as acids and bases. You may have heard that acids are responsible for the sour taste of lemon or vinegar, or the acids can react with active metals like aluminium or magnesium to produce hydrogen gas. While on the other hand, bases are usually associated with a bitter taste and a slippery or soapy feel. We also have the fact that acids can change color of some specific organic compounds or mixtures like litmus, where bases change the color of those specific compounds to different ones. For example, acids change the color of litmus to red, while bases change the color of litmus to blue. While these properties are famous, they are not adequate to identify acids and bases, and we don't use them to identify acids and bases in modern science. We use our modern acid-base definitions or theories to identify or recognize acids and bases. Three common acid-base definitions are the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition. At first, I'm going to talk about the Arrhenius definition. The Arrhenius acid-base definition, proposed in 1884, is usually considered as the first modern acid-base definition. Based on the Arrhenius definition, an acid is a substance which dissociates in water and produces H+ or hydrogen ions, while a base is a substance which dissociates in water and produces OH- or hydroxide ions. In other words, based on the Arrhenius definition, an acid has H or hydrogen in its formula and releases those hydrogens in the form of H+ or hydrogen ions in water, while a base is a substance which has OH in its formula and it is capable of releasing those OH into water in the form of OH- or hydroxide ions. Therefore, an Arrhenius acid increases the concentration of H+ or hydrogen ions, while an Arrhenius base increases the concentration of OH- or hydroxide ions in water. Therefore, we see we have the Arrhenius acid-base definition, in which acids are associated with production of H+ or hydrogen ions in water, while bases are associated with production of OH- or hydroxide ions in water. It is important to notice that in the Arrhenius acid-base definition, the medium is water. we have our acids and bases in aqueous solutions. Water is the solvent and acids and bases are solutes. Where acids are solutes capable of producing hydrogen ions and bases are solutes capable of producing hydroxide ions. As an example, for an Arrhenius acid, we can consider HCl. Hydrogen chloride gas can dissolve in water to produce the aqueous solution of hydrochloric acid. Hydrochloric acid in water dissociates into hydrogen and chloride ions. Since hydrochloric acid in water can produce hydrogen ions, we can consider hydrochloric acid as an Arrhenius acid. As other examples for Arrhenius acids, we can consider other hydrohalic acids, hydrofluoric acid, hydrobromic acid, hydriodic acid, and also many other acids like nitric acid, sulfuric acid, phosphoric acid, and so on. As an example for an Arrhenius base, we can consider the aqueous solution of sodium hydroxide, in which sodium hydroxide dissociates into sodium and hydroxide ions. Since sodium hydroxide is capable of producing hydroxide ions in water, we can consider sodium hydroxide as an Arrhenius base. As other examples for Arrhenius bases, we can consider hydroxides of other active metals like lithium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, and so on. In the context of acids and bases, acid-base reactions or reactions between acids and bases are very important. Based on the Arrhenius definition, acids are producers of H+ ions and bases are producers of OH- ions. H+ and OH- react with each other in water to produce water. Because of this reaction, Arrhenius acids and bases can react with each other to produce water as one of products and a salt as the other product. For example, the aqueous solutions of hydrochloric acid and sodium hydroxide can react with each other to produce sodium chloride as our salt and water. The chemical equation of the reaction is as follows. HCl aqueous, NaOH aqueous yields sodium chloride and water. If in this reaction we consider our substances in their dissociated form, we will have H+ and Cl- for hydrochloric acid, Na+ and OH- for sodium hydroxide, Na+ and Cl- for sodium chloride, and finally water. Now it is easy to see that sodium and chloride ions in this reaction don't change. There are our spectator ions. If we omit these spectator ions, we see that this reaction is based on this one. Or the main reaction behind this is the reaction between hydrogen and hydroxide ions. Arrhenius acids and bases react with each other to produce salt and water because hydrogen and hydroxide ions react with each other to produce water. So, this general reaction, acid and base, yields salt and water. This is the general form of these reactions like this. This reaction is based on this one. We see that in this reaction, hydrogen and hydroxide ions react with each other. They consume each other. They cancel each other. Therefore, we can consider that in this reaction, acids and bases are cancelling or neutralizing each other. And as a result, we sometimes call this reaction a neutralization reaction. Another important point here is to know the real form of hydrogen ions in water. Let's examine hydrogen ions. Hydrogen ions are hydrogen atoms without their electrons. Each hydrogen atom has one electron and loses that electron to form a hydrogen ion. Therefore, hydrogen ions are nuclei of hydrogen atoms. They have a very dense positive charge, and because of that, they easily bond with nearby molecular entities like water molecules. In water, a hydrogen ion combines with water to produce H3O plus or hydronium ion. If we consider the Lewis structure of substances in this reaction, we will have here we can see that in this reaction, in fact, the oxygen atom of one water molecule shares one of its two lone electron pairs with the hydrogen ion and forms a covalent bond with it. Therefore, there is a strong association between water and hydrogen ion in this ion, and we should consider it as an independent entity. So we see that hydrogen ions exist in water in the form of hydronium ions, and hydrogen ions can't exist in their bare form in water. As a result, when Arrhenius acids dissociate and produce hydrogen ions in water, those hydrogen ions readily combine with nearby water molecules and produce hydronium ions. Therefore, Arrhenius acids are in fact producers of hydronium ions. For example, it is better to write the dissociation reaction of hydrochloric acid in water as follows. HCl and water yields hydronium and chloride ions. But for simplicity and ease, we usually write this reaction in this way. But we keep it in our mind that in this reaction, hydrogen ions are in fact in the form of hydronium ions, and they can exist in their bare form. A similar thing happens in other solvents. For example, when solvent is ammonia or NH3, hydrogen ions will combine with nearby ammonia molecules to produce ammonium ions. It is also good to know that even hydronium ions are not the real exact form of hydrogen ions in water. In fact, hydrogen ions in water exist in this form. H2O taken n times plus. We have an association between the hydrogen ion and a number of water molecules. For example, N, which may vary from time to time and situation to situation. We usually consider that here the association between the hydrogen ion and one of water molecule is stronger than others, and therefore we usually consider this as a hydronium ion surrounded by some other water molecules. Or we consider this as a solvated or hydrated hydronium ion. Another important fact to know here is the fact that Arrhenius developed his acid-base definition based on his works on electrolytes and ionic dissociation. Electrolytes are substances which, when molten or dissolved in solvents like water, can conduct the electric current. This is due to the presence of ions in their molten or dissolved forms. Ions come from the ionic dissociation of the electrolyte. Arrhenius was the first scientist to notice this. Arrhenius proposed that many salts in water dissociate or separate into ions, or we have ionic dissociation for them. For example, sodium chloride in water dissociates into sodium and chloride ions. And this is the ionic dissociation of sodium chloride in water. Based on his works on electrolytes and ionic dissociation, Arrhenius developed his acid-base definition, and it is easy to see that Arrhenius acids and bases have a kind of ionic dissociation in water. In the context of electrolytes, they are classified into strong and weak ones. In the case of strong electrolytes, the ionic dissociation is complete or near complete. Concentrations of ions are high, and the molten or dissolved form can conduct the electric current well. While on the other hand, in the case of the weak electrolytes, concentrations of ions are low because ionic dissociation is partial, and the molten or dissolved forms conduct the electric current weakly, or there are weak conductors of the electric current. We sometimes use similar terms for acids and bases. Strong acids and bases are associated with complete or near complete ionic dissociation, while weak acids and bases are associated with partial ionic dissociation. For example, in the case of hydrochloric acid, almost all of HCl molecules dissociate and separate into hydrogen and chloride ions, and almost none of initial HCl molecules remain in the solution. Therefore, here ionic dissociation is complete, and we consider hydrochloric acid as a strong acid. On the other hand, in the case of hydrofluoric acid, dissociation is partial. Some of HF molecules participate in this reaction and some don't. In the final aqueous solution, some of HF molecules exist in their original form. As a result, we consider hydrofluoric acid as a weak acid. Their difference can also be shown by signs. We usually use these signs for for strong ones. This is the sign for a net forward reaction. While for these ones, we usually use one of these signs. This sign is for a reaction in both directions, and this sign is for a chemical equilibrium. For example, we usually represent the dissociation of hydrochloric acid in water like this. But in the case of dissociation of hydrofluoric acid, we use one of these dissociations, or this one. We will later come back to this idea of classifying acids and bases into strong and weak ones. And we will see we usually use equilibrium constants to classify acids and bases into strong and weak ones. It is also good to know some facts from history. Some acids and bases like nitric acid, sulfuric acid were known to humanity from ancient times. Antoine Lavoisier, known as the father of modern chemistry, noticed that the element oxygen reacts with elements like phosphorus and sulfur to produce compounds which give acids in water. For example, phosphorus and oxygen can produce this oxide of phosphorus, which can yield phosphoric acid in water. Lavoisier considered oxygen as the central part of acids. Lavoisier considered acids as some specific oxygen-containing or oxygen-based compounds. In fact, because of this, Lavoisier named the element oxygen as acid former. Indeed, in Greek language, oxygen means acid former. Later, Johannes Jacob Berzelius stated that acids are oxides of non-metals and bases are oxides of metals. This is a general fact usually discussed in the context of metals and non-metals. For example, SO3, sulfur trioxide, is one of oxides of the element sulfurous, where sulfurous is a non-metal. SO3 in water gives H2SO4 or sulfuric acid. So we see oxides of non-metals are usually associated with acids. On the other hand, Na2O or sodium oxide is the oxide of the element sodium, where sodium is a metal. This gives sodium hydroxide in water, which is a base. So we see oxides of metals are usually associated with bases. Despite of the Lavoisier's point of view, scientists noticed that not all acids contain oxygen. Sir Humphrey Davy noticed and proved that acids like HF, HCl, H2S, and so on don't contain oxygen. Later, so Sir Humphrey Davy challenged Lavoisier's idea of oxygen-based compounds as acids. Later, Justus van Liebig stated that acids are substances whose hydrogen can be replaced with a metal. Based on the Liebig's acid-base definition, both of these kinds of compounds can be considered as acids. Based on the Liebig's acid-base definition, sulfuric acid is an acid because its hydrogens can be replaced with a metal, as in this reaction. Magnesium reacts with sulfuric acid to produce magnesium sulfate and hydrogen gas. Also, hydrochloric acid is an acid. because magnesium can also replace hydrogens of hydrochloric acid. Therefore, scientists like Sir Humphrey Davy and Justus von Liebig shifted the idea of acids from oxygen-based compounds to hydrogen-based compounds. Now, based on our discussions, it is possible to assume that the Arrhenius acid-base definition was a combination of his works on ionic dissociation and Liebig's acid-base definition. Arrhenius acid-base definition was a novel step in his times. But in modern science, we usually don't use this definition, this theory, because of its drawbacks or limitations. The main limitation of the Arrhenius definition is the fact that Arrhenius definition considers acids and bases in water, or in fact, Arrhenius definition limits acids and bases to water or aqueous solutions. We will see that we can have acids and bases and their reactions in other situations too. Because of the limitations of the Arrhenius definition, we usually use other acid-base definitions, mainly the Bronsted-Lary definition and the Lewis definition. I will talk about the other acid-base definitions and their comparisons in later tutorials. This is the end of this online tutorial. I hope you find it useful.